So this is me. My name is Dylan. I'm a senior engineer to what everyone else calls staff engineer at CrowdStrike. Been writing code for a long time, 25 years in 4 industries, including a fintech startup working with stock market data. In the past, I did gigs in C++ and C#, some VB, some JavaScript, Java, Python, lots of things sprinkled around. Switched to Go full-time in 2016, and I've been writing nothing but Go pretty much since then. Spent a lot of time in Go for Slack. This is me. You can thank my kids for subjecting you all to that image of me as Princess Leia that you'll never be able to unsee. Also, it's my birthday. So what are we here for? We're here to talk about Goop, which is Go, but with OOP. Many of us, maybe most of us, came to Go from some other programming language. Probably a lot of Java, C++, C#, but like Johnny said, Python, Ruby, PHP, even Objective-C. One of the common threads that run through all of those is a class-based, object-oriented programming model. We all spent a lot of years learning and internalizing those patterns and idioms. Go is a little bit different, though. It was initially designed to make it easy and fast for Google engineers to build and deploy network services. That focus on efficiency, especially developer efficiency, means that if we just apply those OO patterns and practices to writing Go, it can lead to a lot of Goop. We'll start off with some academic background. What is OOP? It's a programming model that grew out of work in MIT in the late 50s and the early 60s. According to Wikipedia, which we all know is the definitive source of unvarnished truth on the internet, the term object-oriented programming was first coined by Alan Kay while he was attending grad school in the mid-60s. Focuses on software systems based on objects that capture state and methods on those objects that manipulate that state. The system behaviors are defined by the interactions between those objects. The idea is that software objects mirror some real-world objects that the software is designed to process. The thing with OO, though, is that we can end up fixating on defining abstractions and creating type hierarchies that implement them in a way that mirrors some real-world scenario. But real life is complicated. As OOP grew, more and more language features and even entirely new languages were added in an attempt to get ever closer to perfection. Unsurprisingly, all those features created software that was harder and harder to reason about. This quote from Alan Kay, y'all remember him? Sums it up pretty well. I made up the term object-oriented, and I can tell you, I did not have C++ in mind. Adding to the fire, in the 90s and the early 2000s, there was a strong push to formalize software development and make it enterprise class. This led to more abstractions that applied to more and more scenarios, eventually getting us to the pinnacle of object-oriented programming, FizzBuzz Enterprise Edition. Uses all 23 design patterns from the classic Gang of 4 book. Everything is insulated from everything else, so the code is maximally flexible. There's logging, there's tracing, there's everything you can imagine. Obviously, not all OOP software ends up like this, but it's not uncommon for things to get complex. Although you can do OO things in Go, Go is not really object-oriented in a traditional sense. It's a practical language. Think meat and potatoes rather than Michelin star. Specific things like Go structs are not classes. Embedding is not inheritance. And packages, not types, are the fundamental unit of design. We'll go into each of these in more detail in the next few sections. First, we'll talk about structs. There are no classes in Go. Go structs are simple things, much closer to a C struct than a Java or C++ class. It's really just a named collection of fields, each with a name and a type. In real-world terms, methods in Go are just syntax sugar for special functions that automatically get an extra first argument. Constructors in Go are also just regular functions named new x by convention that initialize and return instances. They are 100% optional though. We even have a proverb for it. Make the zero value useful is meant to call out this idea that no one has to call your constructors. There are also no destructors. Instances are automatically reclaimed by the garbage collector when they go out of scope. Yes, I know some people out there will say, but we have runtime set finalizer. Yes, that exists, but using it correctly is very often dark arts, so tread lightly. That brings us to our next point. Go also does not implement inheritance. Instead, we have embedding, which is a form of composition. Embedding focuses on what operations the things can do, either directly or via having an embedded instance of some other type, rather than on which kind of thing a type is meant to represent. And since Go is optimized for developer efficiency, fields and methods on the embedded type are promoted to the public surface area of the outer type. That means embedding looks like inheritance if you squint at it just right, but there be dragons. Let's go through a few examples. For the first scenario, we have a simple system with 3 types. There's a base thing that has a do stuff method, and a normal thing type that inherits from it. There's also a fancy thing that inherits from base thing and overrides do stuff. Pretty standard fare for an OO system. It's also valid Go that builds and runs, mostly. All's well at first, we can create instances of all 3 types. They all 3 have a do stuff method, including normal thing inheriting its implementation. We can also see that do stuff on the fancy thing has overridden that base method. So far, so good. Extending things a bit, we add a function that accepts a base thing, following traditional OOP idioms again. And we get the expected result. Yes, this obviously isn't idiomatic Go, but that's kind of the point. Thinking in terms of classes and inheritance kind of does work in Go. But then the wheels come off. We're still in OO mode, and we try to pass a normal thing, which inherits from the base, to our new function, and boom. The compiler is angry at us. It insists that there is no is-there relationship between a normal thing and a base thing, so we can't use them interchangeably, and it suggests we should all go rethink our life decisions. We're dedicated Gophers, though, and we won't be discouraged. We look at the code a bit, and we figure out that we do, in fact, have a base thing right there as part of our T2 object. So we pass that to do the thing, and voila, it's all working. Everything is right with the world again. Or is it? We now take our newfound adjustment for how to do inheritance, and we try to pass a fancy thing to do the thing in the same way. It compiles and runs, but generates the wrong output. The Go compiler is happy to accept t3.baseThing as an argument, but it will call baseThing's doStuff method, not the overridden method on the fancy thing. As we've seen here, Go struct embedding can look like inheritance, and it is in some ways, but the resulting behavior is very often not the same. You can easily end up with a big pile of goop when you have an OO mindset and you think in terms of base classes, derived classes, and inheritance. For our last difference, we'll dive into packages. In Go, the package is really the smallest unit of code. All code has to be defined inside of a package. Every Go source file includes a package declaration as its first line. Encapsulation and visibility are also defined at the package level. Private symbols are visible to all code within the package, regardless of if it's a function or a method on another type. There's no such thing as type-scoped encapsulation in a package. Package can also be as small as a single variable declaration and as large as you want to make it. Importing a package brings in the whole package, which means consumers will need to build the entire thing. It's an example of how this can get really bad. We had a package where we were doing some code generation. Over the years, that package grew to several thousand types. Downstream consumers were seeing extremely long build times, 7, 8 minutes, and 80 megabyte binaries. It was getting ridiculous. We looked at it, did some refactoring, did some research, and we figured out that many of those consumers were only actually using a handful of types, in a lot of cases, only one. We reorganized the package and the code generation to emit categories of types and a package for each category. By doing that, we went back and reorganized things. The consumers now were compiling in less than a second, and the binaries were back down to 7 or 8 megs for those small consumers. And finally, as we all know, references to any symbol in your package will include the package name or your import alias in the consumer code. Your struct type or function is never named in isolation. The package always qualifies everything. Now we'll dive into a few examples of Goop and see what happens when you directly apply those OO patterns to Go projects. First, the first one will be creating a separate shared component in order to resolve codependencies. This is one of the classic examples of refactoring, where you take two components that depend on each other and break them apart. The canonical fix is to define a third component with the common parts, then update the first two to depend on the new thing instead of each other. In abstract computer science terms, that's absolutely the right thing to do. But doing it in the OO way can make things worse, not better. So to set the stage, we have a foo service that depends on another service bar. Foo communicates with bar via bar's exported client. The bar team works in the next building over. It turns out they need to access foo, so they import foo's client. This is perfectly valid Go. Everything will build and run since there's no package import cycle. It's a hidden problem though, because there is a circular dependency between the two modules. The current version of foo depends on some version of bar, which depends on an earlier version of foo, which depends on an earlier version of bar. Yeah, it's fun. So we put on our OO refactoring hat and dive in. Let's make it better. We create a new clients module with interfaces for the foo client and bar client. Everything is nice and clean and refactored. We check it in, we cut a release for our new module. Then we circle back to our two services. We update them to reference the new client's package, and we're done. Neither service depends on the other. Problem solved, pour the drinks. Right? Yeah, well, this is technically a successful refactor. The two modules no longer depend on each other. It's not actually that great if we dig in a little. New components that refactors like this create are very often reduce cohesion in the system. Now the owners of each service have to also maintain their client in this other module. They also create unnecessary coupling. Other consumers of foo now also depend on bar, and vice versa for bar's consumers. When either interface changes, every client of either service will see an available update for that new client's module. And because they lack cohesion, these components also end up difficult to name. As we all know, along with off by one errors, naming is one of the 3 hardest things in computer science. In this case, we call the new component clients, but that doesn't really convey the functionality that that package provides. It says what kinds of things it contains. And lastly on this topic, this refactor has introduced a third Go module that will need to be versioned and released over time. Since each service is now effectively spread across 2 Go modules, developers will have to manage Go workspaces and coordinate releasing 2 modules separately in the right sequence with each change. And we really made things better. So how do we tell whether we're being good Gophers or we're creating Goop? Here's a few signs. First would be if the refactored component has a package name like client, base, or interfaces that doesn't represent some piece of functionality. Or we've defined a package that doesn't actually provide any functionality. It's just a place to hold definitions for things that are actually used elsewhere. And finally, the system we ended up with has more moving parts and requires more effort to maintain than we did when it started. In our second example of Goop, we'll talk about something many of you are probably thinking about right now: interfaces. Declaring an interface to insulate consumers from concrete implementation is probably even more common than refactoring into a shared component. It's an excellent pattern, even in Go, but how that pattern is defined is important. Interfaces, or abstract base classes in class-based OO, are a core tenet. They list the available operations on some component. Importantly, they have no implementation, they're only declarations. As we mentioned before, typical use case is to insulate consumers from providers. Consumers code to the interface, they don't depend on the provider directly at all. Class-based OO often also includes types declaring which interfaces they implement explicitly. This can lead to goopy code, though, with tightly coupled, harder to maintain modules. As an extreme example of how things can go off the rails, the AWS SDK for Go contains a client API interface that contains every possible S3 operation, 91 methods. And let's be honest, most of us really only use list objects, get object, and put object. For a more likely scenario, let's say we're working on a new service that provides CRUD operations plus some higher level queries. Remember, we're still wearing our OO hat, so we start with the abstraction. We create a service interface with create, get, update, and delete methods for our foo entity, then var, then baz, so on. Add in a dozen or so queries. By the time we're done, the service interface has almost 60 methods. Once we have the interface defined, we start writing code. First comes the service impl struct, because we call the interface service, and a new service constructor. We implement create foo and so on and so forth with a full suite of unit tests. We check everything in and tag the first release. Moving over to the consumer side, we import our new server and we start calling it. Pretty quickly, we need some diagnostics, so we write ourselves a print foo function that dumps a record to the terminal by giving its ID. As conscientious Gophers, we also accept a server.service interface that we use to retrieve the data. Some of you are out there thinking, so what's the problem? And you're right, this is fully functional, and we even have an interface that we can mock for tests. But this isn't really the Go way. Go interfaces are conceptually different than OO. They still define some set of behavior by declaring one or more methods, but they are automatically satisfied by any type with those methods. There's no need, or mechanism for that matter, for a type to explicitly declare that it satisfies any interface. The real nugget, though, the difference is that in Go, the consumer should be defining an interface, not the provider. On the surface, this is a very subtle distinction, but it's also a powerful one. By defining interfaces at the consumer, not only is the consumer decoupled from that specific provider, but it's insulated from any provider implementation. It also simplifies testing, because tests only need to mock the specific methods being called. Remember, we don't care about 87 of those methods in S3. Maybe most importantly, consumers defining interfaces eases future development. Provider code you write today can satisfy many interfaces, including ones that don't even exist yet. You can also extend provider code without impacting existing consumers. No need to update your exported interface, which Go modules has taught us is a breaking change and a major version bomb. With these differences in mind, let's revisit our code. In the consumer repo, we define a new foo getter interface. We've eliminated 50 plus methods because we only care about the one. And we update our print foo function to take our new interface rather than the server's exported interface. the actual service implementation can still be passed in, but importantly, this code no longer depends on it. So again, how do we know if we're creating Goop? Well, the first one is if you use the good name for the interface. Since you used the good name for the interface, you had to decorate the actual implementation type by adding an impl suffix to the end. Looking at all you Java developers out there, we know who you are. Stop it. You have an interface that redeclares every method on an implementation, which means it needs to be updated anytime any new functionality is added. And finally, there are no references to this interface you just defined in the package that declared it. In our third example, we will visit everyone's favorite bike shed, project structure. How should I structure my project is a very common question in the Go community. There are lots of opinions floating around about what's good or right. Everything from reading standard library code to excellent advice in blogs from Ben Johnson and lots of others. The Go team even put a blog out a week ago with their own high-level guidance. On the other end of the spectrum, however, there's a certain GitHub repo with a name that includes both Golang and standards with some questionable opinions. Since we're talking about OOP here, though, we'll attack it from that angle. There's tons of research and prior art, but have I mentioned before that Go isn't really OO? We'll take a look at some of these patterns for how to avoid stepping in Goop. One of the most common patterns, certainly the one I've used the most in my own work, is clean architecture. Clean architecture was defined by Uncle Bob Martin around 2012. It's a way of organizing software systems with clean boundaries that minimizes coupling and makes them easier to maintain. It's a combination of several other patterns like hexagonal architecture, onion architecture, ports and adapters, and other references like clean code with a focus on practical guidance for building systems. In a short outline, clean architecture defines 4 standard layers. The entities, which is our core domain that has no external dependencies. In Go, that means only depends on the standard library. Do not import anything else. Use cases, which is our business logic implemented in terms of the domain. Interfaces and adapters, which transform data between the internal domain and external systems. And frameworks and drivers, which are those integrations with external systems, databases, the network, end users. We all hate them. There can be more layers, but those 4 cover most systems. But the important part is dependencies can only point inward. Each layer fully insulates the next inner layer from the rest of the world. Obviously, these are all good ideas. Following these concepts will more than likely lead to better code. Similarly, maybe less common in Go, but prevalent in the wider software industry is model view controller, model view presenter. Same ideas, but more focused on building UIs. There's the model, which is our core domain data types. The view, which is a visual representation of all or part of the model, and controllers are presenters that process input to update the model, then trigger those views to re-render. Very common pattern in web applications. Again, good ideas all, but the trick is to avoid the Goop. So here we have a couple of examples of projects that applied clean architecture and MVC, following the examples you would see online. Those of us that came from other languages have seen these kinds of project structures many, many times. I even created one when I first started writing Go. I came from C#, where we were doing ASP.NET, which at the time was very much MVC turtles all the way down. Like the other 2 examples, though, they don't feel like idiomatic Go. Packages are named for the kinds of things they contain, and they mirror the layer names from the corresponding pattern. The types are often repeated in each package. And any kind of domain or model change requires updating multiple packages in the project, sometimes every package. It's maintainable enough for one project if you're already familiar with the structure. Pretty rough for cross-project integrations, though. The generic package names usually mean that consumers will have to alias their imports if they reference more than one dependency. And the code for any given type is spread across multiple packages, so it's harder to find, harder to deal with. So these architectural patterns are well known and widely used for a reason. The people who define them are some of our industry rock stars, and the ideas are all good. I know I keep saying that Go isn't OO, but that doesn't mean it can't be a little bit OO. We just need to accept that prior wisdom without just stamping out the patterns. Think about them and apply them in Go. So here we have another project. It still follows a clean architecture pattern, but not literally. The project's domain is defined at the root of the module, so the types are no more goop.foo rather than domain.foo. Other packages represent bounded context, which is really just a fancy way of drawing a box around some chunk of functionality and adding a label to it. But using bounded context groups code by functionality, not kind, so packages end up with better cohesion. It also lets us define the same type in different layers using the right name. We can have a no more goop.user and a database.user. They're both users. They're both defined correctly. They mean different things because they're in different contexts. We've collapsed the interfaces layer into our Goop service package. Remember, consumers define interfaces. We don't need to create a dedicated package for them. We define a data store interface that defines the data layer operations used by the service that will be satisfied by the DB implementation in our database package. And finally, our Goopy application bootstraps things by creating an instance of database.db and passing it into our new service function as a dependency. We built a full project that includes and builds on all that wisdom of the past while still being idiomatic Go. We have clean boundaries, well-factored code, and there's not a domain or use cases package anywhere to be found. Our last bit of Goop may be the most famous acronym in object-oriented programming, SOLID. SOLID calls out 5 principles that should be applied to produce good code. But the examples out there are often couched in class-based OO terms. But like the architectural patterns in the last section, there's still good advice for Gophers. We just need to adjust our thinking a bit. First, there's a single responsibility principle, which says there should never be more than one reason for a class to change. Go doesn't have classes, though, so first thing, we replace class with package. Then we follow the advice of one of our own Gopher wise ones, Mr. Dave Cheney. Avoid packages with names like base, util, or common. Those packages will inevitably contain more than one thing, unsurprisingly violating the single responsibility principle. The open-close principle states, software entities should be open for extension, but closed for modification. This one tends to be a bit vague, but the gist is that we should be able to provide new behavior without needing to modify existing code. In Go, consumer-defined interfaces and implicit interface satisfaction make this pretty straightforward. By not pre-declaring and exporting contract interfaces, provider code can be extended to add new methods and provide new functionality. Since consumers only depend on their own interfaces, there's no disruption when new methods are added to the provider. Things stay stable. Next is the interface segregation principle. Clients should not be forced to depend on interfaces that they do not use. Pretty simple. This one is kind of second nature to most of us Gophers because this is precisely how much of the standard library is defined. Interfaces like IOReader, IOWriter, JSON marshaller are defined by the packages that use them and only have a single method. Again, remember the proverbs. The bigger the interface, the weaker the abstraction. When we do need larger chunks of behavior, we combine these narrow interfaces. IO read writer is both an IO reader and an IO writer. By defining interfaces this way, any given consumer only depends on the exact behavior that it requires. The Liskov substitution principle says objects of a superclass should be replaceable by objects of a subclass without affecting the correctness of the program. Since we don't have classes in Go, again, we swap in interfaces. Consumers define interfaces and structs satisfy them implicitly by providing the right set of methods. And because interfaces are satisfied implicitly, the consumer doesn't depend on any implementation, not even the base one. And finally, the dependency inversion principle, which is simply depend on abstractions, not concretions. Everyone can probably guess what comes next. That's right, interfaces again. Most of us have seen some variation of accept interfaces and return structs. In Go, it's very good advice. By declaring interfaces for our input parameters, we're settling our dependency on the required behavior, not on any concrete implementation. Similarly, by returning instances of structs, we allow our consumers to decide which behaviors they require. Structuring things this way gives us maximum flexibility and minimizes coupling. Before I wrap up, who noticed that the last 5 slides were out of order? I ended up talking about soiled, which is like solid, just with a lot more goop. So to actually wrap up, many of us came from object-oriented languages like C++, Java, C#, Python. Go is a different kind of language, though. As I hope I've shown you today, blindly applying those past OO experiences and using those patterns and idioms without adjusting them for Go can lead to a complex, hard-to-maintain mess. We can do better, though. Take the time to learn about why those OOP patterns exist and what problems they were meant to solve. The implementations of those patterns in Go can be significantly simpler than in traditional OO systems. They just look a bit different. Honestly, one of the hardest parts of learning Go for me was unlearning what I had been doing for almost 18 years writing OO code. I did it, though. It takes some effort, but we all can. Like I mentioned at the start, Go is a practical language where heady abstractions often make things worse. Keep things simple, avoid creating goop, and become better Gophers.